Okay, so let's work on example 3.4 from the OpenStax textbook. Let's first read the problem. Consider the motion of a particle in which the position is given by x of t is equal to 3.0 t minus 3t squared meters. In part A, they ask us what is the instantaneous velocity at 3 different times, and in part B, they ask us what is the speed at those same 3 times. Okay, so in order to interpret how do we solve this problem, where do we start, we always want to just first write down what is our known. Right, so the major thing that they tell us in this problem is this equation. They tell us the position of the particle at any moment in time is equal to 3.0 t minus 3t squared meters. All right, so you could plug in any time into this equation, and you would therefore know the corresponding position at that time. I'm actually going to rewrite this formula such that it makes a little bit more sense in terms of the proper units. So I can tell that that first unit of that 3.0 constant must be meters per second, right? Such that 3.0 meters per second times time in seconds, those seconds would cancel out, and that would give me something in meters, right? So we're measuring a position here, it better give us something in meters. I can also tell that that second constant, 3, is 3 meters per second squared, right? Because when I multiply it by t squared, the second squared from the t squared would cancel the second squared from the meters over second squared, and again give me something in meters. Alright, so I first wanted to just rewrite that equation in a way that is a little bit more clear. Okay, so now we have the position of a particle at any moment in time. If you wanted, you could graph this. Alright, this is a graph that would look something like this. At time equals 0, you could plug in, I get 0 minus 0, so I'm definitely at position of x equals 0 at that moment. Here I'm graphing position versus time. And I can also plug in time equals 1 to this equation and see I have 3 minus 3, and so I'm definitely at position of 0 at time equals 1 second. Okay. And it turns out in between, what does this do? It goes up like this and comes down like this in a parabola. All right, so this is a position as a function of time that they tell us in the problem. Okay, so now we can actually start thinking about how do we answer the problem. What is the instantaneous velocity at these 3 different times? Well, we have to think about what is the relationship between velocity and position. We know that conceptually velocity is how far you go in a given period of time, right? But we also know that instantaneous velocity is like when your position and velocity are continuously changing. What we want to do is we want to figure out what is the slope of the tangent line of our position versus time graph at any given moment. All right, so if I want to know the velocity at time equals 0, I need to draw a tangent line at that point and figure out what is the slope of that tangent line, and that is equal to my velocity. If I want to figure out what is my velocity at time equals 1, I need to draw a tangent line at that moment in time, I figure out the slope of that tangent line, and that is my instantaneous velocity. Okay, so that's how we think about it graphically. How do we do that numerically or with our equations? Well, we know that what I described, the slope of the tangent line, is our definition of the derivative. Right? So if we ever want to find our velocity, and if we know our position as a function of time, we just have to take a derivative of that. So I'm going to take the derivative of this big equation that we had just written down. We have 3.0 meters per second times time minus 3 meters per second squared times squared. Okay, so when I take that derivative, that first t just goes away, so I have 3.0 meters per second, and I can check that has units of velocity, so that's a good thing. And then I have minus 3, derivative of t squared is 2 times t, so this gives me minus 6 meters per second squared times t. All right, and I can check again when I plug in some time there in seconds, multiply it by meters per second squared, I'm going to get meters per second, which is my proper unit of velocity. Okay, so I've derived an equation for velocity at any moment in time. Okay, and that's a great thing. So okay, I can see this as a linearly decreasing curve. I can plug in time equals 0 and immediately see the velocity at that moment is exactly 3.0. I can plug in any later time and see that the velocity is going to be going down, 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 go to 0, and then become negative, right? Because this term here is definitely just going to make this velocity smaller and smaller and smaller and more negative as time goes on. Okay, So now that we have this, we can just plug in any time and figure out the corresponding velocity at that moment in time. All right, so if I plug in time is equal to 0.25 seconds, as they ask us to do in the problem, the velocity, and in this notation I'll be using, I'm just going to say the velocity at time is equal to 0.25 seconds is equal to 3.0 meters per second minus 6 meters per second squared times 0.25 seconds. All right, so we have 3.0 meters per second minus 1.5 meters per second, and we end up with an answer of 1.5 meters per second. Okay, so that's one of our three answers to this problem. Okay, if I go ahead and solve the other times, I have some room over here, so perhaps I'll use that. If I plug in time is equal to 0.50 seconds, I find that my velocity at that moment time is equal to 0.5 seconds, is again equal to 3.0 meters per second minus 6 meters per second squared times 0.5 seconds. So that gives me 3.0 meters per second minus 3 meters per second. And so I end up with the velocity being 0 at that moment in time. And that looks like it kind of makes sense from our plot of position versus time. Right? At time equals 0.5 seconds, that looks like the slope of the tangent line at that location is 0. Right? That's where we're turning around. That's where the velocity is 0. Okay? And finally, we can plug in time is equal to 1.0 seconds, and I find the velocity at that moment in time is equal to 3.0 meters per second minus 6 meters per second squared times 1 second. And I get this equal to negative 3.0 meters per second. All right, so at that moment in time, the velocity is negative. Okay? So we're pretty much done with part A now. We've got our three answers for part A. For part B, what is the speed of the particle at these times? Well, we can remember that speed is just equal to the magnitude of our velocity vector. And so at time equals 0.25 seconds, that's a positive velocity, so that implies the speed is also positive. It's exactly the same number. At time equals 0.5 seconds, the speed is also 0. And at time equals 1 second, well, this time the speed is equal to the magnitude of the velocity, so that makes the speed equal to 3.0 meters per second. Okay, so that's a nice problem. They also, I think, give us some graphs for this problem. Let's take a look at these. And here they are. So it's nice that they provided these in the example in the book. And again, our position versus time graph looks like an upside down parabola with us starting at position x equals 0, moving out to some greatest position. We turn around at time equals 0.5 seconds. We return back to where we started at time equals 1 second, and then we start moving in the opposite direction, speeding up as we go, moving further away from where we started. From the velocity versus time graph, it should match our equation for velocity versus time, where at time equals 0, we have a velocity of positive 3 meters per second, right, and that corresponds to the slope of the tangent line at that moment in time of our position versus time graph. At time equals 0.5 seconds, we've stopped. Right, so we've slowed down at a continuous rate from our initial speed of 3 meters per second to our till the time we get to 0.5 seconds, and so that's corresponds to the slope of the tangent line at that location on the position versus time graph. By the time we get to time equals 1 second, we're now traveling at minus 3 meters per second. Right, that corresponds to the slope of the tangent line at that moment on the position versus time graph, and you can see we continue to move in the negative x direction, just speeding up and speeding up and speeding up, moving faster and faster in the negative x direction. Okay, and then if we want to plot the speed as a function of time, well, speed is always positive, right? So speed is the magnitude of our velocity. So from 0 seconds to 0.5 seconds, it looks exactly the same as our velocity versus time graph. But once we have negative velocity, we have to have correspondingly positive speed. Right? So this looks like it has a kink in it, and our speed is increasing and increasing and increasing as time increases there.